Hi folks, this video segment is about discussing the concept of periodicity condition in the Catia program. This is within the finite element module of the Catia program. In some other software and in finite element literature, this may be referred to as cyclic symmetry. As far as the toolbar where this appears in Catia, it's in the virtual parts toolbar. And that's, of course, in the generative structure analysis, the FEA module. And it looks like that. It's called periodicity condition. And when you click on that, you will be asked to make certain selections. We'll get to that in a few minutes. Now, I'm going to do two problems for you. One of them is what you see here. And basically, it's a steel plate. And the edges got some holes. The edges of the steel plate are all clamped, and it's subjected to a downward pressure, as you can see here. Now, when I do this problem for you, if we model the entire thing, which is a very simple problem, when we model the whole thing, you're going to have gigantic stresses around these edges, and basically what we're saying is that we have welded that entire structure to something else at these edges, and therefore it's not unexpected that there's going to be huge stresses in these circles. But that is not the point. Okay, so later on when I do this problem, I'm not going to fix the edges. I'm going to fix the interior of these. But that's not really the issue here. Now, if I did this thing with the edges fixed, the entire disk, I may get some pattern of stress like this, one meter stress like that, and a displacement of this type. Okay, I didn't put any scales here because in this video we're not discussing the accuracy and mesh refinement at all. It's just the concept that I want to describe to you. As I mentioned to you, because the edges are fixed in this particular drawing, there are huge stresses around the holes, the edges of the hole. I'll do this problem, but not the entire thing. I'll show you how you can use periodicity condition to reduce this. And then I'm going to come back and do the same problem, except that you can pretend this is a flywheel that's spinning in space at some given RPM. There's a subtle difference between this problem and the one that I showed you as far as the boundary conditions go. However, not as far as the concept of periodicity goes. So let's discuss the issue of periodicity condition, or cyclic symmetry for either one of these. It really doesn't matter which one you take. So it really doesn't matter. So let's pretend that this was the one that with the edges were fixed, applied to pressure, or it was turning. It makes no difference. Now, first of all, notice that if I take, because there's 8 holes here, because if I take a cut like that, and this cut is going to be 45 degrees, then I can solve the problem only for this nice sector where these faces, side faces, actually remain plane. The side faces, if you take a cut here, they were plane, and because of the nature of the problem, they think about it, before the deformation is a plane, after the deformation is a plane. So as if these were on roller condition. Catia doesn't call them roller, it calls them surface slider. Or I could have taken actually another plane here through that. So instead of doing this problem, taking 1/8 of it, we could have taken 1/16. Because notice that because of the way symmetry works in this problem, this is before deformation is a plane, after deformation is plane. So is this, and so is that. Okay. However, I don't have to take a nice symmetric cut like that. I can take a cut, still 45 degrees. If we are doing this problem, still 45 degrees. But you don't have to have these lines passing exactly halfway between the two circles. So this plane, side plane, is not going to stay plane because of lack of symmetry, it actually warps. And so does this one. However, whatever happens here is going to be happening right on that, because notice that this edge, this piece, is immediately next to another piece where the left side of the piece that is over here is the right side of the piece that we are modeling. So this and that, they behave exactly the same way as far as the stress, as far as the displacement goes. Okay, but there are, you should not use surface slider here or there, because these are not going to stay planar anymore. Okay. Now there are two, there's two warnings here. Don't use surface sliders here, because that doesn't apply. However, these edges also must be identical as far as the size is concerned and as far as the topology is concerned. All right. So, for example, if you go to this problem, which is again 8 cutouts instead of holes or like that, you can take any sector. This has to be 45 degrees. That's the only constraint. In other words, this line could have been rotated. This entire thing, this entire sector could have been rotated by some amount to the right, by some amount to the left, and it's okay. Don't put surface sliders here, but these are periodic boundary conditions. Okay, but you cannot take like that, because if you look at the sides that you take here on the left and on the right, they are not identical, and therefore this periodic or cyclic symmetry does not apply. So first, let me go ahead and solve this problem for you. And I have some dimensions here that I'm going to stick to it. So let me go and make a piece like that. Okay, let's go to Catia. On a convenient plane, on that horizontal plane, I will sketch. Oops, not there. I will sketch a sector like that. So how does it look like? For example, let me see. These are simple enough geometries that I can do it for you. Like so. Okay, let's clear it up. Get rid of this, get rid of that, get rid of this. Let's make this thing 45 degrees. Okay, and I'm going to draw my dimensions. Okay, so this was 6 inches. Okay, let me draw my circle here. Something like this, and the distance from the center of this to that point was 4. Okay, and the diameter of this was 1 inch. Okay, and since it doesn't matter where the circle is located, it does not have to be exactly halfway between two. I shifted a little bit to the right so that you don't need a very fine mesh. Okay, exit and pad it. I think here I said that the thickness of the plate is half an inch. So we pad it by 0.5. Okay, good. And we're going to make this thing out of steel. Go to generative structure analysis, analysis and simulation, generative structure analysis, and there is the mesh. Well, we'll keep it as why don't we make it parabolic? Okay, parabolic. and I'll keep the size as it is. Okay, so let's go ahead and apply our conditions. Now, remember, what I said is that instead of applying a clamp to the edge, I will apply the clamp to the face, okay? It's just that it's practically applying it to the edge is not feasible. Okay, there. So this entire face of the hole is clamped, okay? And we're going to apply pressure to this, pressure on that face, 20 psi. Okay, good. There we are. Now, obviously, if I run this thing, it will run, but you will not get the correct. This will run. If I run it, it will run, but you will not get correct information because this face will not behave like the other face, and it should. That's exactly. These are periodic. In other words, whatever happens here is going to happen on the other side, as far as displacement goes, for example. So, of course, I'm not going to run this, but I will apply the periodicity condition. See that? It says individual parts toolbar right there. This one says periodicity condition. It asks you for the two faces. Let me uncheck that. It asks you for two faces, this face and that face. Try it again. This face, this face, rotate, and that face behave exactly the same way as far as displacements go. Okay, this is the icon for periodicity. Okay, so let's run it. All right, and let's look at for example, the deformation. Okay, let me animate it. Okay, let's look at the displacement. There's a displacement. Let's use average ISO. Okay. Now you get some weird stuff here inside of that. These are the periodic, the constraints that Catia automatically puts, that stuff on this side and stuff on that side are the same. If you don't want to see these internal elements, so double click on that and say, just show me the elements for you know, the solid elements. Don't show me all those external ones. Let me hide these things too, so you can see better. Okay, this is the periodic boundary condition. I'm going to hide, and this hide. There. Okay, and if you look at the von Mises stress, it looks like this. Okay, believe me, if you did the entire object, all 8 sectors, and you did that, you're going to be getting, as long as the meshes are the same, you're going to be getting the same answer. As long as the two meshes are sufficient, you're going to be getting the same, almost the same results. Okay? Now, you might say, okay, if that's the case, well, what's the big deal about this other problem? The reason I want to do this other problem, there's a subtle issue that I want to bring it to your attention. Okay? So in this, I cannot show you for this problem because of the nature of the boundary condition. But here, it's going to reveal itself. So let's go ahead here and let's go to Catia. Oops. Let's get rid of these. First of all, these plots. Delete, delete, delete. And let's go to the load. Obviously, this load is wrong, and this strain is not the same. Okay. First of all, we want to tell Catia that this is rotating about the axis here at a certain RPM. So here is the in the load. This is centrifugal load. There is under rotation forces. You select it. Support is anything that you pick is going to be entire body, because centrifugal force is a body force. Rotation axis is going to be that edge on the side, okay? And notice that it puts an icon like that. And 1000 RPM, 1000 turn per minute, okay? And it's going at a constant speed, so there is no angular acceleration. All right, good, good. Now, we know that this side and the other side have periodic conditions. So select this side, just like before, turn it around, that side, periodic. Now, if I run this, it will bomb out. And let me show you why. First, let's try it. It will bomb out. And if you say, okay, I know that it didn't run, but can you tell me why? So if you say, show me the deformation, it looks like that. And if you animate it, you see that there are no restraints here. So this is a rigid body, basically motion. So let's see how we fix this. There is an easy way to fix this, and there is a longer way of fixing it. First, I'm going to do the longer way, and then I'm going to come back and do it, show you how you can quickly do this. Okay, so let's deactivate this. All right. Now, first of all, we know that there is a plane of symmetry in the middle here, and I can use that. I can use that plane of symmetry, cut this thing in half, and put it on the surface slider. But I'm not going to go that route. I want to go a different route, okay? So what I do is, let me hide these things so that you can see what happened here. Okay, let me hide these things. Okay, so I'm going to say, you know what? This point, to avoid rigid body motion, I'm going to say that it is fixed in all three directions. By the way, I could have clamped it, but that's okay. So translation in the three direction is 0. Now, if I run this thing, it will again bomb out. You'll see. Let's try it. It will again bomb out. Let's see why. Look at the deformation. You can see that still it swings as a rigid body. It cannot go up and down. It cannot float in space, but it can still hinge about that point. So good. So what I'm going to say is fine. So you know what? Why don't I fix one point here and prevent it from moving in the direction, for example, in this case, direction Y. So do not move in direction Y. Okay? Let's run it now. Oh, it worked. So let's look at the deformation, and let's actually change the scale so that we can see it better. And let's animate it and look at the view from the top so that we can see what happened. There we are, view from the top, animate. It looks like that. Notice that these faces warp out. If you say, show me the stress, that's what you get. This is what you expect. When you have a disk with a hole like that, rotating at 1000 RPM, 8 of these, the biggest stresses are going to be at the corners of these, at these location of the hole. Now, this thing that I did, notice that what I did, I fixed a point here. I fixed a point here in 3 directions. This one in 1 direction. This is a modified version of the 1, 2, 3 rule. Whenever an object moves in rigid body, if you want to take the rigid body motion away, if it's applicable, if it's not a dynamic problem, then you can use the 1, 2, 3 rule. The reason here that it actually was not 1, 2, 3 It's because of that periodic boundary condition. Okay,